Can thermodynamic diagrams help us visualize heat transfer processes? Have you ever wondered how we can make sense of heat transfer in different systems? Thermodynamic diagrams are here to help us visualize these processes in a clear and straightforward way. Let's break it down together. Thermodynamic diagrams are graphical tools that representing key properties of thermodynamics. They show how heat energy moves and changes within a system. Two common types of these diagrams are the pressure-volume diagram and the temperature-entropy diagram. The pressure-volume diagram, often called the PV diagram, illustrates how pressure and volume change during processes like compression and expansion. It helps us visualize the work done by or on the system. The area enclosed by a cycle on this diagram corresponds to the net work output or input. While it mainly focuses on work, it also gives us clues about heat transfer by showing how volume changes affect energy. On the other hand, the temperature-entropy diagram, known as the TS diagram, directly relates to heat transfer. Here, temperature is plotted against entropy, which measures disorder or energy dispersal in the system. The area under a process curve in this diagram represents the heat transferred during that process. For instance, when heat is added, the curve moves in a way that increases both entropy and temperature, clearly indicating energy input as heat. Conversely, when heat is rejected, we see a decrease in these values. This makes TS diagrams especially useful for analyzing cycles in power plants and refrigeration systems, where heat transfer is essential. These diagrams also help us identify specific thermodynamic processes. An isentropic process, where entropy remains constant and no heat is transferred, appears as a vertical line on a TS diagram. An isothermal process, where temperature remains constant, is shown as a horizontal line. This visual distinction helps us understand how heat and work interact at different stages of a cycle. In practical applications, engineers and scientists use thermodynamic diagrams to design and optimize systems such as engines, turbines, and refrigerators. By visualizing heat transfer and work interactions, they can improve efficiency and performance. This makes thermodynamic diagrams not just educational tools, but also practical aids in real-world applications. These diagrams simplify complex energy interactions into clear visual forms. They provide a way to see invisible processes like heat flow and entropy changes, making it easier for learners and practitioners to grasp fundamental principles without needing advanced mathematics right away. In summary, thermodynamic diagrams, especially the temperature-entropy and pressure-volume diagrams, are powerful tools for visualizing and understanding heat transfer processes. They translate abstract concepts into graphical forms that reveal how energy moves and changes within systems.